What's up? All right. Let's make sure everything's working all right. That's not working right because I'm getting my own audio. That's not what I want. Let's see. That's better. All right. Let's see. So I'm gonna jump back here. I gotta run my tablet script quick. Should probably have done this before I started streaming. There we go. All right. Well, guys. All right. So today we are talking about section 3.3. We're going to get into it. So in section 3.3, we're going to begin our discussion of Laurent Series and singularities. This will be a really cool section, in my opinion, at least. I think it's kind of dope. It'll be less proof heavy in my presentation. I'll try to avoid doing as many oh, here's like some technical proof, because a lot of them are not really that insightful. Just kind of like, honestly, like in the Taylor series one, it wasn't like, it's cool to see the trick. It's cool to know how Koshi's theorem can be used with some weird geometric series kind of thing, and then you can build out a Taylor series, and it's great. But the actual nitty-gritty of doing the proofs themselves, I'm not trying to say it's not important. What I'm trying to say is that it is sufficiently full of technicalities that it distracts from the overall story, which is really cool. So I'll leave it to the textbook, which does a fine job presenting it. And if you are interested in the nitty gritty of the arguments, I will, let you can always go look at it. I'm not stopping you. No one's stopping you. I'll give you the general idea of how the proof goes, but we're not going to really focus on some of the bigger proofs in this section very much, because they basically go along the exact same line as the Taylor series proof and aren't really that cool. I mean, they're cool. I don't know. They're big deal results, but the results are cool. The proofs are not. Happens sometimes, right? Not trying to hate on the authors. I'm just trying, or the people who came up with these things in the first place. I'm just saying that, like, it's not as cool as the results, which is maybe the biggest compliment you can give to a theorem. So we're just going to start it out straight up with the Laurent expansion theorem. That is, unlike in other things, we're not even going to do this like gradual, like, let me introduce a concept and let's build up to it. I'm just going to give you the thing. The Laurent expansion theorem, theorem 3.3.1 in your textbook, is cool. It's a long theorem to state it out, but let's do it. So we're going to grab two radii, R1 and R2, greater than R1 greater than or equal to 0, and R2 greater than R1. We'll grab some point Z0, and we'll look at the region A for annulus, the set of all Z and C between the circle of radius R1 and R2. So this is like a little open region. I'm gonna they say see figure 3.3.1, but I'll just draw this sucker right quick. Why are all my brush sizes wrong? Weird. Anyways, basically just think of this. You got two different little circles, and what we're looking at is oh, well, that wasn't what I wanted. We're looking at this little region, right? The area between them, right? This is A, an annulus. So that's like a donut shape, right? Like a little ring here. So this is an annulus, a region A between R1 and R2. Cool. And to highlight where those things are, just to be clear, it's like this is R1 and this is R2, right? Okay, all good. Setup. We also can allow R1 to be 0, obviously. Why are we giving me trouble here today? Keeps losing my settings. So weird. We of course can allow R1 to be 0 or R2 to be infinity, or we can allow both. Totally fine. don't get hung up on anything like that. What we're talking about is we're talking about analytic functions on these regions. Okay, if you have a function that's analytic on these regions, here's what the Laurent Expansion theorem claims. It claims that you can write, and this is, I'm gonna make that a little, yeah. You can write f of z as a sum of two series. One of them looks like a good old-fashioned power series right here. The other one looks like a good old-fashioned power series, except now the z part, the z minus z naught to the n piece, is on the denominator. It's just like a power series, but flipped over into the bottom of a fraction, right? So what we're claiming is that both series converge absolutely on A and uniformly in sets of the form B row 1, row 2, where these guys are, let me make my highlighter slightly better size, B row 1, row 2, which is the set of points within a distance in little annuluses about inside of our set, right? So we're gonna grab row 1's bigger than R1, and row 2's smaller than R2, and row 1 smaller than row 2. So we're just looking at these guys kind of, right? So the idea here is basically just to keep our little picture going, maybe, and I should have maybe drawn this a little tiny bit bigger. We'll see how it goes. That's good enough. So like little annular regions inside of here, right? Oh, screwing that up, whatever. Here, I'll just make it a thick annulus. So like, like you could look at some like little, you know what I'm saying? Like it's like, I'm trying to say that there are, sides to this, right? It's not just a simple line. Like it's got an inside and an outside edge. You see what I'm saying? But it still stays inside of there. So like a little sub ring inside of that ring. You get what I mean? So B row 1, row 2, these little rings, that's where we get uniform convergence of this kind of like doubled up power series. Okay, this series is called the Laurent series, as you might imagine from the Laurent Expansion theorem. You also call it the Laurent Expansion, whatever you want to call it. You're expanding it out into a sum. All right, and of course this is around Z naught in the annulus A. So it's basically a Laurent series around Z naught, about Z naught, for Z naught in this region. And of course the Z naught matters and the region matters. All right, so what are these terms? After all, the Z's and Z naughts and N's and all that, that just comes automatically. What are these ANs and BNs? How do we actually write an analytic function on an annular region like this? Well, the cool thing is that if we grab gamma, get back to using my highlighter, if we grab gamma, a circle around Z naught, the center, with radius r, where r is between the two things, this would be actually just like a little circle in there instead of like a little sub-annulus, right? Just like a little line in there, like a little circle right there, right? Then the coefficients are just given by this deceptively similar to the derivative via Koshi's integral formula and all that terms right here. So if we were looking at a Taylor series for a function that was analytic on, the entire region or at Z naught or something like that, right? Then we could definitely say, hey, wait a second, this is like the nth derivative of f at Z naught, right? But the trick here and the thing to remember is that, and let me write this down over here. It need not be the case that an equals the, something like the nth derivative z naught or something, that whole business, right? So it need not be the case that we're, getting like the Koshi integral formula business. Or really, I should write this over like n factorial or something like that. As in the power series. Notice it totally, it could be, right? It doesn't have to be. And that's the kind of business here, is that you have this cool thing going on where we're just going to basically borrow one way of writing the derivative that you get from Cauchy's integral formula, right? And then in situations where Cauchy's integral formula maybe doesn't actually apply, we'll just keep that well-defined term that would be equal to the derivative were that reasonable. And amazingly, everything still keeps working. That's super cool. So these ANs are like this, and as you can imagine, the BNs just are exactly the same, but now you can basically say that the BNs are equal to like a to like the minus n's, right? Or not a to the minus n, a sub minus n, right? The minus nth term if you extended this from positive integers to negative, right? And so in this case, you're just bringing the z minus c naught up instead of down, right? So the BNs just are really the exact same as the ANs. There's nothing fancy at all going on here. We're just doing exactly the same thing again, but using negative values of n. Okay, and you can see this down here. Bn is negative an. So any pointwise convergent expansion of f of this form equals the Laurent expansion. That is, the Laurent expansion is unique. So let's kind of zoom out for a second, because holy crap, what a long theorem right here. It is meaty. This is the real deal. This is when it starts getting pretty cool, in my opinion. The Laurent expansion theorem, and what we're going to get today and tomorrow, is when you start to see some of the really neat stuff. One way to think about all of this is, if you take like the Bn as negative an business, this piece here is basically, or kind of take this over here. This piece here basically is like the sum from n equals negative infinity to positive infinity of an z minus c naught to the n, assuming like down here we let n's be negative for negative n, you know what I mean? So this is just like a double-sided power series, which is kind of cool. It seems so deceptively simple to say it. When you look at it like this, you're like, oh, well, yeah, why was I only using positive powers? Why wasn't I doing polynomials with negative exponents for, like, why was I looking at like z plus z squared plus c cubed, that kind of thing? Why wasn't I using z to the negative 1, negative 2, negative 3, and so on in my expansion? Like, how many more things can you write? And this is why the Laurent expansion theorem is cool, because it starts to explore that sort of obvious extension of the classic power series idea. After all, we get like a ton of stuff from looking at power series, right? Power series are just so mad useful. When you've seen them before in regular calculus, they're all over the dang place. They are a wonderful little tool. It basically lets us use all the tricks we like to use for polynomials and stuff like that in a setting other than for polynomials. And now what we're really doing is we're saying, hey, what about rational functions, right? What about ratios of things that are like polynomials? And indeed, that's what we end up getting. We'll talk about it soon when we get to meromorphy a little bit later, talking about meromorphic functions. But really, this is all about exactly the same kind of thing as you get in rational functions. This is about, it's slightly more general, in fact, but for the most part, for many things, this is basically like looking at rational functions where the numerator and denominator are instead holomorphic, or analytic, as we've been saying. Analytic functions in the numerator and denominator. This is what we're going to be able to kind of extend all of our stuff into talking about. So we've got these nice formulas right here, the Laurent expansion theorem. If you want to prove it, there's a great little proof in your book. And by little, I mean it's multiple pages long, and it relies on worked examples and some kind of technical results we didn't really do from previous sections. It's got a bunch of annoying little pieces, and it basically kind of follows some of the same sort of tricks that we did when we were talking about Taylor's theorem. So it uses Koshi's theorem, things like that, and a weird geometric expansion, geometric series, an expansion of some rational piece into a geometric series, a ratio, and then it does some other stuff too. We don't, like I said, we don't need to care about this. There are more interesting things to get to, just exploring what the deal is with all this stuff. So I'm not going to waste a ton of time proving a long thing that doesn't really offer a lot of insight. I do encourage you to look at your book. It is a good proof to at least glance at. I can bring it up in a bit if we want to, but let's just get an idea of what we're even kind of talking about here. So let's think about an example here. Let's start by letting A be, say, the set of Z and C such that I shouldn't even use a bar there. I'm going to use a colon for the such that the modulus of Z is greater than 1. Let's look at this set, right? And let's let f of Z be given by, what's a good example? 1 over Z times Z minus 1. How about that? Yeah, that's fair. That's fair. Okay. Now let's just do a basic Laurent expansion. So you might be saying, how are we going to do this? Are we going to calculate all of these terms right here? Are we going to do all these ands, all these bns? Oh my God. No, nothing like that. We're just going to use some basic facts. And then from the uniqueness of the Laurent expansion, we'll know that we've already actually calculated all of those, which is kind of cool. So let's do a Laurent expansion. Let's just do, so we got 1 over Z times Z minus 1. All right, fair enough. Let's pull out a minus 1 over Z. Man, all the flowers are blooming out here, which sounds wonderful, but I swear I'm allergic to every single one of them. Anyway, so you plot a minus 1 over Z, and this is 1 over 1 minus Z. Geometric series, that's what we're going to do. So this just turns into, am I doing this right? Yeah, that should be fine. Let's even actually pull out a, you know what, let's pull out a Z squared, how about? So, well, wait a second. I think I meant to do this on the other direction to start with. Yeah, that's what I messed up on. Yeah, all right, here. Here, yeah. I was attempting to be too cool. Yeah, that's what I did wrong, dang it. Yep. Okay, anyways, I'm gonna pull out, yeah, let's do this. This is fine. One over Z. Yeah, okay, here, I'll just leave it like this. This is all good. Let's do this. All right, 1 over Z. Messed myself up on that example. Dang it. And then I'll just pull out a Z here. How about? So I'll get 1 over Z right there. Minus 1. Yeah. You know, I didn't even need to pull out a minus. That's what I did wrong. What a simple mistake. Here, I'm going to switch this up. All right, we're just going to start over this piece right here. Oof. How about it? All right, I'm not even going to take it. Here we go. From the top, how about it? Okay, so I'm going to pull out a 1 over Z right quick, and then I have 1 over Z minus 1. All right, fair enough. You'll all buy that. Then I will I'll leave that 1 over Z sitting out here. Now notice I can write this as 1 over Z times 1 minus 1 over z. Notice 1 over z in modulus, at least, is, no, this is right. I shouldn't have erased that earlier, greater than 1. So this is less than 1, right? Cool. All right, so now I can just pull out that 1 over z squared, and then I have a 1 over 1 minus 1 over z. Since that's a less than 1 modulus, I'll write this as a nice little series right here, a geometric series, 1 plus 1 over z plus 1 over z squared plus 1 over z to the third plus da-da-da-da, all on and on. And hey, what at the end of the day do we get? Well, this just says, I'm being a little sloppy with my equal signs here to save space. This just says we got 1 over z squared plus 1 over z to the third plus 1 over z to the fourth plus da-da-da, on and on forever. All right, so if we look in terms of how this business right here is, all of our ANs in that case would be 0, and all of the BNs are going to be, say, what? 1, except for B, the first one right there, right? Since we don't have 1 over z here. Okay, cool, all good. Now, so this is the Laurent expansion of f on this a about 0, right? All right, cool. Now, what if I chose a different domain, right? What if I did the other direction, right? What if I looked at what if I do like b equals, say, z and c, such that we're looking at z between 0 and 1. Both of these nice little annular regions. In this case, in A, the radius of the outside part of the annulus is infinite, and the radius of the inside part is 1. All right, here we have the radius of the inside part 0 and the outside part 1, right? Okay, now do the same expansion again. We're going to do the same trick. Obviously, we can just basically carry this exactly over. Just plot a minus 1 over z in this case. This is where I was throwing myself off before. Ooh, I am lagging extremely bad right there. That was weird. Anyways, let's take out a 1 over z minus 1 over z, and then I'll have 1 over 1 minus z, and since z is less than 1 in modulus, this gives me exactly the geometric series again, and so I'll get minus 1 over z times 1 plus z squared plus on and on and on. And of course, this just turns into minus 1 over z minus 1 minus z minus z squared, and so on, minus forever, right? Okay, and notice these are totally different looking series, but they are Laurent expansions of the same function f, just on different domains, but about the same point. So there is 3 things that we have to keep track of. There are 3 things. Oh, grammar. We have to keep track of the domain, the function, and the point. Here we have the same function, same point, different domains, so we get different expansions. These expansions are unique, but only relative to the choice of these 3 things: function, domain, and point. So choose a different point, different domain, so on, you get different things. Of course, the point kind of comes automatically with the domain, since these guys are annuluses, right? The center of the annulus is kind of automatically given, right? So really it's just about function and domain, but just to be kind of clear, this is the business of it. We want to you get the point automatically when you choose your domain, and so on, but so it's really just relative to the function and domain. But to be clear, the point seems like a reasonable thing to discuss as well and put in there. Everyone gets it, I hope. Anyways, that whole business aside, let's talk about singular points. This is kind of the entire idea why we would maybe care about a Laurent expansion, why we would even want to do something like this. The entire reason for it, the business you're going to get is that you can deal with singularities. Exactly like our example right here. Wow, I zoomed in pretty good. All right. Like this guy, f of z is 1 over z times z minus 1, right? Here we've got, I think I am lagging out. Huh, internet. Let's see. I hope that's working better. I think it is. Okay. Who knows? We're not even defined at 0, right? And so this is kind of we're able to deal with singularities. Places, you know, where you throw a 0 in the denominator, right? And so isolated singularities, we ended the last class talking about the isolation of singularities in terms of Taylor series and all that stuff. We're going to start classifying singular points. All right, so, or isolation of zeros. Now we're going to talk about kind of the reverse concept of isolation of singularities here. Now, the gist of everything, let me pull up my lecture notes. Well, we'll talk about it in a moment. Let me just give it like this. Let's look at the basic case of when R1 is 0. This is like what we looked at last time in the second case, right? Here we're looking at an annulus where the inner radius is 0. So that is, you have like just, you know, no radius. You're just missing a point right at the middle, right? Here you had a, you know, one of radius r equals 1, right? And it's centered at 0. Okay, so something like that. This case is one you encounter a lot, right? What about like functions like 1 over z and that sort of thing? In this case, f is analytic on, well, you know, by assumption, we're looking at analytic functions on annular regions. So it's analytic on such an annular region, but it's just basically a disk with the point z0 cut out. It's a deleted R2 neighborhood of z0. That is, it's a disk of radius R2 about z0, and then we just cut out that center point. I don't think I need to redraw that. You guys can imagine it, but if you want to see a picture, it's in your book, right? It's exactly what we just drew down there. So circle with a little point cut out of the center. Cool. Now, these guys we're going to call isolated singularities. That is, we're analytic and all good everywhere except at this little point right in the middle. It's isolated, it's all by itself. Isolated singularity. Now, when we expand f in a Laurent series, this just is our classic Laurent series. We've got our regular Taylor series looking chunk in one direction, and then in the other direction we've got our Taylor series but with something in the denominator looking chunk. Okay, and this is obviously valid on our annular region. All good. We're going to classify what this whole thing is like. All right, what different cases can occur? All right, so if f is analytic on a region A, I'm going to not use red. That looks pretty obnoxious right there. I like blue better. If f is analytic on a region A that contains some deleted epsilon neighborhood of z0, then z0 is an isolated singularity. We just said that. Okay, so this situation, right, in terms of a Laurent expansion. All right, if z0 is an isolated singularity of f, and if all but a finite number of the Bn are 0, that is, if we don't have these dot dots going on and on forever in any meaningful way, that is, there's only a finite number of terms that have stuff in the denominator and are not 0, then we're going to say that z0 is a pole of f. If k is the highest integer such that bk is not equal to 0, we're going to call it a pole of order k. This is kind of like when we were talking about zeros of order k last time, right? Where you looked at the first term on the Taylor series side of things that was non-zero. Now we're just looking at the, kind of the opposite way. The terms over here, when it instead of looking at the first place, sorry, my dog is barking up a storm. Asmov, come on, buddy. All right, instead of looking at the first term that's non-zero here, we're looking at the last term that's non-zero here, right? Kind of just basically always looking at like the leftmost relative to these two chunks, the leftmost term that's non-zero, right? So if we go and then we eventually hit some point where it's everything afterwards is zeros, like if Bn was zero or non-zero and everything after that was zeros, then this would give you a pole of order n, right? Similarly, if we're talking about zeros of order n and all that, then we're going here and we're saying, oh, maybe A0 is 0 and A1 and A2 and so on, right? Up to some AN, and that's the first non-zero piece, then that's like the leftmost non-zero piece. Similarly, Bn is the leftmost non-zero piece. So poles and zeros of various orders, same rule to determine them, leftmost non-zero coefficient. All right, fair. Now, we're emphasizing here that k is not equal to infinity. We'll occasionally say that a pole has finite order, but we're really assuming always if we say pole, we mean a pole of finite order, right? Now, first order poles are particularly important. They kind of come up a lot, and they're so nice, we're going to call them simple poles because they're really simple to work with. If you only have one term involving something in the denominator, that's great, right? Real easy. It means that you could just multiply by z minus z naught and then, turn f into a regular old-fashioned Taylor series, right? Cool. And in fact, we will talk about that in a little bit, doing exactly that. Part 2, if an infinite number of BKs are non-zero, that is if there is no leftmost non-zero coefficient, we'll call Z0 an essential singularity. Sometimes people will call this a pole of infinite order. When we say pole, we don't want to always have to specify the order. We'll say pole to mean pole of finite order, and we'll say essential singularity to mean a pole of infinite order, right? So essential singularities do some really cool and weird stuff. And as you can see from our example here, you can get essential singularities in situations that are relatively mundane. Like this guy right here, this f, if we expand it on the domain A about 0, which once again is superfluous to say, A is an annulus, so we're expanding it about its center, and the center automatically comes with it being an annulus. But if we expand it that way, notice we get essential singularity right there, right? Notice you got these z's in the denominator for all the terms. In fact, you have no, all the a's are 0, in fact. But all right, so essential singularities. B1, this first piece right here, right, the part that goes over z minus z naught, is so important we give it its own name. We call B1 the residue of f at z naught. All right, cool. So the first coefficient on the rational side of the expansion is the residue. All right, so we'll discuss like historical reasons for why it's called the residue in a little bit, but right now, we'll discuss that tomorrow or on Friday actually, yeah, next class. But right now, it's just a name. We're just assigning a name to it, nothing weird. If all the BKs are 0, then we'll say that Z0 is a removable singularity. This kind of situation is just to distinguish when you basically have an analytic function, except potentially at a point, right? A great example of something like this would be like here, what about the function f of z is z over z? This is 1 everywhere except at 0, right? Oh, so it's basically the constant function 1. We've just got a little hole punched out of it. And notice that singularity, it really doesn't need to be there. It's just there almost by accident. It's just there because we can't really cancel like we naively want to, right? And so we have our own little name right there, removable singularities, just because these guys aren't really that interesting. You can just remove the singularity and sort of get rid of it. So we have our own little name, just a definition. All right. Now, a function that is analytic on a region A except for poles in A, we'll call these guys meromorphic in A. Meromorphic as opposed to holomorphic. I'm now forgetting what the Latin root of meromorphic means. What is that? What is the etymology of meromorphic? Yeah, okay. Hollow means whole, while mero means part. Yeah, okay. Yeah, right on. Okay, good. So you can think of holomorphic, or as we've been calling them, analytic functions, as like wholly good, while meromorphic ones are partially good. They have a part that's good. This part is good. This is the other part, right? Meromorphic, or you can think of them as it's analytic except for poles. It's good except for these parts, right? So if we say f is a meromorphic function, generally we just mean that f is meromorphic on all of C. That is, if we don't specify the region of meromorphy, then we just are kind of assuming it's C, unless we're being in a situation where it is particularly clear what we're talking about. So all of this is just terminology. Nothing weird is going on so far. The gist, and I guess I'll throw one more piece of terminology in here, is that if you have a pole of order k, imagine you've got a function f of z that can be written on some domain A as something like bk z minus c naught to the k plus so on and so on, all the way down to like b1 z minus c naught plus a naught plus a1 z minus c naught. These guys are always so annoying to write on out. Plus, I don't know, it doesn't have an essential singularity or something like that, just a pole of order k. So that means that bk is the leftmost non-zero coefficient in this this part with the z's on the bottom, right? What this piece is really measuring, right? And we call this piece the principal. I have to look. Is it principal? Yeah, principal, not principal. Not with an LE. Yeah, principal part of f at z naught. So this little chunk here, the so-called principal part, this guy measures how singular z naught is, right? Or how singular f is at z naught, right? How much of a singular point, how much of a singularity z naught is for f. This business here tells you that, and so it's like if you just had this chunk, it's like b1 over z minus c naught. If you had a pole of order 1, a simple pole, it's like it's not that singular, you can sort of think of, right? Well, if you have an essential singularity, it's like as singular as it could possibly be. And it's kind of what we're going to explore, is what is this notion of being sort of singular versus not singular. This is just all sort of intuitive jargon I'm throwing around right now. But why is this the right way to think about it? And what do residues mean? What does all of this mean? So let's start exploring it, and we're going to really get into it tomorrow on Friday with some super cool stuff. But the first one is great because this is essentially the beginning of an analog to Koshi's theorem, if you want to think of it like that, for meromorphic functions. And Koshi's theorem is applicable in certain situations to meromorphic functions. Remember, we could deal with functions that were analytic except potentially at some given point, and we could do a bunch of stuff with, like, okay, well, we can still use Cauchy's theorem and all that, right? So that was really the beginning of our our treatment of meromorphic functions, though we didn't know them by that name yet. But and so some people who maybe have already taken this class or seen this before, we're trying to be we're relatively pithy on their homework, and did a little bit of this in homework assignments and kind of annoyed me with it. But they used this result. This is a great result. It is you can see some of our previous things with Cauchy's theorem as giving us this, or you can see this as the beginning of a Cauchy's theorem for meromorphic functions. So proposition 3.3.3 says that if we have f analytic on a region A that has an isolated singularity at z0 with residue b1 at z0, then if gamma is any circle around z0 and A whose interior, except for the point in z, lies in A, mouthful. So think about it like this. You've got gamma, a circle around z0, everything, the circle and everything inside of it is inside of A, except potentially that middle piece, right? So the interior is in A, except maybe the center of that circle. Then the integral of f about gamma is b1 times 2 pi I. Another way to say this, if you want to just kind of write it out, if we use the term, I'm gonna put it up here. If we write like res f z0 equals b1, right? If we write residue like this, then, and some people put the z0 first, I don't know which you prefer. The way to think of it is that and hey, doesn't this look kind of like Cauchy's theorem? Yeah, this sort of looks exactly like it. It's telling you that the residue and the index have something to do with each other a little bit. So let's do an example. What this really lets you do is it lets you use a Laurent expansion. At least right now, what this is like, the purpose of it, the useful trick you can do with it is that you can compute things using the Laurent expansion. You can compute contour integrals using the Laurent expansion. And this is kind of cool. This is sort of nice. So for example, let's let f of z be equal to like e to the, I don't know, 1 over z, right? We know how to write that out as a Laurent expansion around 0 or something like that, right? I mean, after all, it's the exponential function, and we've just made flip the z, right? So z to the minus 1, right? So we should just be able to take and do this as 1 plus 1 over z plus 1 over 2 factorial z squared plus 1 over 3 factorial z to the third plus, and so on and so on. That is, we just have z to the minus 2, z to the minus 3 up in the numerator. Yeah, nothing fancy is going on here. It just plug it into the exponential function. All good. All right, so if we do this, what can we see? Well, just start looking at it. Okay, these chunks here and so on, these are our b's. And what is our b in the first b1? It's 1, right? No. So the integral around any circle about 0 of e to the 1 over z is equal to what? 2 pi I, yeah? Since b1 is 1. Huh. It's kind of cool. And this is for gamma, any circle with center 0. Cool. All right. So kind of nice. We can actually compute some stuff using this this nice little theorem. This is a pretty cool and useful piece. Namely, notice we didn't require that we had a pole or anything like that. Indeed, in this case down here, we have an essential singularity because we have infinitely many terms with z's in the denominator. Yeah. Infinitely many terms with a non-zero coefficient that have z's in the denominator at least. So this is an essential singularity. Now, this gives us some stuff, and we're going to use it to characterize types of singularities a little bit more. And this is what we'll start to get into next time. And I'll just kind of give a rundown real fast. We'll look at analytic functions that have isolated singularities, and we'll get a whole bunch of different little characterizations of what types of isolated singularities can occur. We'll talk a little bit about what I was saying before this last bunch of definitions, which is that if you have like simple or like removable or, you know, poles of order k or something, you know, if you have a pole of order k, like right here, notice you can multiply f by z minus c naught to the k, and all of these guys, you just get bk, and, you know, like all the rest of it just turns into a nice Taylor series, right? Or it looks like a Taylor series at least, yeah? Just a power series. You should expect that it actually is basically a Taylor series. It's a power series, and it seems like everything's all good, yeah? And so that sort of tells you that having a pole of order k is sort of like having a 0 of order k. And this this equivalence, or this way of thinking about things, is totally reasonable. And what this will let us see is that meromorphic functions are, like I said, ratios of holomorphic functions, or analytic functions as we've been calling them. That is, take an analytic function divided by another one. Hey, how about that? You've got a meromorphic function. Now, essential singularities are a lot weirder. So essential singularities, we stop having meromorphy, and these guys don't act all nice like this. Everything is a little bit weirder at essential singularities, and we'll get one of the coolest results, the Casorati-Weierstrass theorem, which we will definitely prove because it's awesome. Now, that will be a nice little story to tell, and then we'll begin to do a whole lot more stuff using these techniques. It'll be it'll dramatically expand our toolbox and make certain things that we had to do before through annoying means, where we, like, you know, cut little keyhole like slots around zeros and stuff. We won't have to do stuff like that anymore. We'll just actually be able to deal with essentially fractions in the complex world, you know, or rational functions, and that'll be really, really useful. So cool. We'll get into that a lot more next time, and I think this is a good place to call it for today. Awesome. See you next time.